Welcome to a lesson with Dr. Powell. We're going to take a look at the chain rule for derivatives. So we've noticed that derivatives are simply matrices. And the way that we interact with actually using the derivatives to go from run to rise is a matrix multiplication. So kind of like inputting run and putting it into rise is matrix multiplication. And so when we have maybe a function of another function, so we kind of have like f of g of something else, then kind of what happens here, we have this inputting. So you take this and this inputs into f. And since it's an input into f, this right here is, so if we can find a rise of g, well, that rise of g actually becomes the run that we put into f. Now, how do we put a run into f? In this case, for derivative-wise, it's a matrix multiplication, which means precisely all we're doing is we're just taking the derivative of g as a matrix, and we're multiplying it on the right side where the input goes to the derivative for f. So quite literally, if you have f of g, your result is just going to be, the resulting derivative is just df times dg. Basically, if you have composition, derivative just turns that composition quite literally into multiplication. Now, think about this for a minute. If g has, okay, let's suppose that g has two outputs. That requires that f will have two inputs. So that's fine, because if g has two outputs, remember that outputs are always represented by rows. So if we have two outputs here in dg, and we have two inputs for f, the inputs are now columns. See how this matches with this? That allows us to be able to take dot products and allows this to be completely well defined. So pretty much this always works. You can always just take this derivative and that derivative as matrices, do a matrix multiplication, and voila, you get the new derivative. That's essentially all the chain rule is, in a sense. Let's actually look at an example. Suppose, for instance, that we have the following. Suppose that we have x, let's do x to the y. Okay, so that's our function. All right, and suppose also that we have another function going on here, and we do x of t and y of t. So this is kind of like a parametric type function, which you could think of it as a vector if you want. So I'll write it in both ways. X of t is equal to cosine of t, and y of t is equal to, let's do sine of t. All right. So, okay, so we could think of it as a vector, cosine t, comma, sine t, where this is x. Okay, so that's what x is and that's what y is. All right. So this is what we're going to do. All right. So we have this function. Let's kind of think about f for a minute. Let's think of f, and this other one, let's think of this as g. Let's say g of t. It's like a vector output function. So let's do f and let's do g. So f has one output and has two inputs. G has two outputs. Notice how it outputs a vector here. And it has one input, t, right? Okay, so let's write f, the derivative of f, okay. And it's one output means one row, two inputs means two columns, and we can do this. It's just the regular one. It's just fx, fy, right? So we take the derivative with respect to of this with respect to x, thinking of y as a constant. So y is a constant, so it just comes down, y, x to the y minus 1. Okay, and then this one means that x is a constant. We'll take the derivative of that. That's natural log of x times x to the y. I mean, this is like saying 2 to the y. Take the derivative of that. That's natural log 2 times 2 to the y. But we're just, instead of 2, we're thinking of x. So we get kind of that idea. Okay. So this right here is our derivative of f. Now our derivative of g, 2 outputs, that means 2 rows. 1 input means 1 column. We take the derivative of g. So the derivative of g right here, this would be, well, since this is just a vector and we have 1 input, right? So for this 1 output, we take the derivative with respect to x. So basically just taking the derivative with respect to, or t, I guess. So basically we're just taking the derivative of t of this and that, just like for a vector, it's just a vector function like we have before previously. Take the derivative of this with respect to t, and that with respect to t. So derivative of this would be negative sine t. Derivative of this would be cosine t. Then just multiply these two matrices together. And okay, multiply the two matrices together. And maybe perhaps we could actually use this if we want, since we're plugging this cosine and sine into x and y, we can actually replace the y and the x with those guys. So we can think, when we do a dot product, we'll just kind of also replace these guys in. So that y is really sine t. Then we have cosine t raised to the sine t minus 1. All right, but that's multiplied with the negative sign. So that would be sine squared with the negative. Okay, so that's the first part. The dot product that times that is this. Then we add this times that. So natural log of cosine of t. And okay, then we have cosine t raised to the sine t. And then we multiply all that by cosine t, which is the same thing as, I don't have enough room here. Let's see. Let's write that down a little better here. All right, so what was that? That was cosine raised to the sine. But then we multiply by cosine again. So it's just like adding 1 to the exponent, because we're just putting another cosine t multiplied in there. Okay, so that's the result. So basically what we did is we took the derivative of this function, of the composition of this function and this one. This one had 2 outputs, this one had 2 inputs. But the result, notice you have 1 input and 1 output. We actually did a problem from single variable calculus, believe it or not, just now, where what we did is we are actually looking at the function f of t, if you will. It's really f of g, literally, but let's just look at what f of g is. So f of g, and we plug in t, and we're looking at cosine of t raised to sine of t. And then what we did is we just took the derivative of this function as is, and the derivative of this function, it's a function of a single variable, but multivariable calculus gave us a slick way of thinking about this via matrix multiplication. And we ended up just getting this. And this is the result. There are various ways of doing this for single variable calculus. You could first do take natural logs of both sides, and then take, like if you had like this is equal to y or something, take natural log of both sides, change that exponentiation to multiplication, do some chain rules and some other things, and you end up getting something a lot like this. Kind of a fun idea that you don't have to do that. Instead, if you kind of use the interaction between the derivative of f and the derivative of g, but in a multivariable sense, and think of it as a composition of 2 different things, where this is like a chunk and that's like a chunk, then you arrive right here at the actual derivative. Thanks for watching.